Quantum computing is a new form of computing, very different from what we're used to, in that it uses something called a qubit. If you think about normal computing, we use a bit, which is either a 1 or a 0. In quantum computing, a qubit can be a 1 and a 0 at the same time. So you can actually test lots of different algorithms and lots of different numerical spaces, all simultaneously. This is what really gives the power for quantum computing. Some of the areas that we're interested in using this would be things that are by themselves, by their nature, quantum. Things like quantum chemistry, trying to compute how a certain molecule might behave, or perhaps leading to new material discovery. What types of alloys could you create? These sorts of simulations we can do today on supercomputers for very small cases. Quantum computers would allow us to do this for much, much larger molecules, much, much larger material spaces. Another area we're interested in looking at is how quantum computing and machine learning might work together in sort of two different ways. One is, could quantum computers help us search very large data sets and very large spaces to zero in on areas where we could then use machine learning and AI technology to continue to advance our cognitive work? The other direction would be, could you use machine learning to help us in designing quantum computers? One of the biggest challenges in quantum computing is the errors that the qubits experience. Could you use machine learning to understand the patterns of errors you're getting and then use that to help eliminate those errors in the future? A quantum system is very different than a normal computing system. As you can see here, we have a prototype of our 50-qubit system. The whole part of this system is really about isolating the quantum computer chip itself, which is right down here in the bottom of this canister. The rest of this is all about isolating it from thermal or electrical or magnetic noise, as well as routing signals in and out of this chip. So at the very top, that is a very balmy 4 Kelvin liquid helium temperature. As you continue down, it gets colder and colder, and by the time you get to the bottom here, it's at 10 millikelvin. That's 10,000ths of a degree above absolute zero. And keeping it that cold is key to making sure you don't get too many errors or decoherence of the qubits themselves. The various wires here are routing signals into that chip to actually manipulate the qubits and actually do the quantum calculation itself.